there is an equal and opposite reaction force. All right? How does this definition compare to the one you've probably heard before? What's different about this version compared to one you may have heard elsewhere? Who's heard Newton's third law before elsewhere? Jackson, you look like you've got a thought. This is just some kind of strange stretch? Okay. Okay, so you're on the right track. So force isn't typically the word that's used. Frequently, it's for every action, there's an equal and opposite reaction. Okay? But action and reaction are too vague and broad. Way more things get incorporated into actions and reactions. And then we don't see what Newton's third law is actually talking about. Newton's third law only applies to forces. And therefore, it's forces that occur in pairs, not actions. We can see this if we look at the free body diagrams that we've been drawing. So I'm going to go ahead and draw one here for a situation we've talked about repeatedly. A block sitting on a table. So with a block sitting on a table, what forces, or what would my free body diagram look like for the block itself? What forces should I draw? Gravity. Gravity. And what else? Normal. Good. All right, force normal. Now, I'm going to take this one step further now, and now I'm going to ask what forces are acting on the table. All right, force normal, caused by what? Caused by the floor, right? So I've got some kind of force normal. What else is acting on the table? Gravity, definitely. Anything else? Absolutely, force of the box. So we've got the force of the box, the gravity, and the normal force all acting on the table, and the normal and gravity forces acting on the box. Now, in this diagram, we've drawn two different free body diagrams, but there's only one pair of forces that are an action-reaction pair. Which pair of forces do you think would be equal and opposite to each other? There is no friction on here. Which forces do you think could be equal and opposite? For which force normal? Okay, and well, this is caused by the table and this is caused by the earth, so nope, that can't be. Other thoughts? Which one would be equal and opposite to the normal force? If you've got a guess in your head, go ahead and give me the guess you're thinking. If you're just staring at it blindly waiting for me to tell you the answer, you're going to be waiting a while. Which one? There are two forces of gravity on this picture. Zane. Gravity of the table. So the table pushes up on the box the same amount that the earth is pulling the table down towards the earth? Amara? So this force normal to this force normal? Why do you think that? Okay, they're both going the same way. But Newton's third law said they should be opposite. Jack. Why? Lucky guess? Okay, so in the normal force, what's pushing up or what's causing the normal force? The table. What's causing the force of the box on the table? The box. All right, so this is an action-reaction pair, and the first thing I want to point out is they're acting between two objects. One force is acting on one object, the other force is acting on the second object. So, action-reaction pairs exist between two objects. Between two objects. They have to be opposite in direction, and one force has to act on each object. Now, if I had a little bit better drawing skills, I would have made this arrow the same length as this arrow, and we would have been able to say they were also equal. But because this is the force that one applies to the other, or one object applies to the other object, that's my action-reaction pair. I could have another action-reaction pair if I started talking about the Earth as well, but we're not going to do that in this case. Doing one more example, Newton's third law is also the reason we can walk. Reason for walking. And if I just draw out a shoe here, better than I thought it was going to be. Okay. We can pick out what forces are acting on the shoe. So, what forces are acting on the shoe? Force gravity. So, if you're ever thinking, oh, I don't really ever participate, I should really say something in class from time to time. When I ask what forces are acting on something, just yell out gravity. All right, what other forces are acting on the shoe? Force normal. That's really the other go-to one that you're never going to be really wrong unless it's floating. All right, so force gravity and force normal. So that'd be if it was sitting still. Now let's talk about if we're walking. So if I'm walking in this direction, what other force is going to be present? Friction, I heard it. Which way is it acting? Almost unanimously, you all said backwards. Because friction is a force that opposes motion. But that's not right in this situation. So it was a good answer. But think about it this way. Why am I able to move? If I remove friction, do I have a chance of moving? No, I mean, like, stand here. If I could do the moonwalk right now, that would be pretty sweet. Because it would be about right how I would move, like how I'm moving. I would try to walk, and I really wouldn't go anywhere. However, turn on friction, and I can start moving forward. So when I'm walking, I am applying a force to the ground. I'm pushing the ground back that way. According to Newton's third law, what then must also be true? It has to be pushing onto me as well. So if I push the ground this way, then the ground has to push me that way. So when we say which way is friction acting? Well, actually friction's acting in the way that you're walking. Because the friction force from the ground acting on your feet is pushing you forward, trying to prevent your feet from slipping. Without friction, your feet would slip. So friction has to act forward here. All right, so our free body diagram on the shoe as you are walking looks about like that. However, just like in the previous one, what forces exist on the ground here? Force normal, definitely. What's pushing up on it, though? And we're talking about the ground. That's the force normal here. The ground's pushing up on the shoe. But is anything pushing up on the ground? I mean, more ground underneath it. So if we really wanted to, we could say force normal. It's not wrong. What other forces are acting here, though, on the ground? Yeah, is that a hand or? Yeah. I'm starting to jump at anything that looks like a hand starting to raise. Other thoughts? What forces are acting on the ground?
Gravity.
Gravity's a good answer. I mean, it's got to be pulled in at some point, otherwise parts of the Earth would start floating away. Anything else? The shoe. The shoe's pushing down on the Earth. Force of the shoe. Anything else? As you walk, are you pushing on the Earth in any direction?
Yes.
Which way?
So right.
Well, yeah, it's kind of like that way, right? So we've kind of got both the force of the shoe being pushing down and pushing back. So I'm going to write force applied. All right. In this situation, we've got two action-reaction pairs. Now, you guys did say force of gravity because there's Earth pulling more Earth down. And you also did say force normal because there's Earth underneath the Earth, like underneath the floor, pushing up on that part so it doesn't just fall in. Yeah, those exist. What are my action-reaction pairs in this case, though? Right, force friction and force applied have to be an action-reaction pair. As you push back on the ground pushes you forward, which is what allows you to walk. What other action-reaction pair have to exist here? Force normal and force shoe. So as you're pushing down on the floor is pushing up on you. Okay? So again, noticing that in each of these cases, one of my arrows is blue and one is green, meaning that they're applying to different objects. Also notice that the forces are acting in opposite directions in each case, and if I was any good at this, the arrows would actually be the exact same length in each case. So, in an action-reaction pair, we see the pairs exist between two objects. Pairs point in opposite directions. Point in opposite directions. And pairs have equal length arrows. Have equal length arrows. All right, questions about Newton's third law? Okay. So now we're going to get to the concept that you guys all wanted to jump to for the daily question, which is momentum. Momentum itself is not an explanation for why something moves forward or why something pushes back when you throw it forward. Momentum is a way that we can try to understand how fast it goes, but Newton's third law is really the explanation for why it's happening. So when we're talking momentum, how many, or not how many of you, but where have you heard momentum used outside of a science classroom? Sports. So if you've got a team that's winning a whole bunch, they say they've got a lot of momentum. All right? How else? How else have you heard momentum used? How so? Okay. No, possibly, but I'm not sure. Don't know the context you're talking about. A car, sure. When a car gets going up to a high speed, then it's going to frequently, they say it has a lot of momentum, so it's going to get over a hill, or it's going to be hard to stop. Other ways that momentum is used outside of the science classroom. Like when you're on the swings, you want to get more momentum to go higher, absolutely. Other ways that you've heard it used outside of the science classroom. Roller coaster. So again, you want to have enough momentum to get over the next hill. Any of these kind of ideas. When we talk about momentum in common language, usually we're actually talking about inertia, an object's tendency to resist a change in motion. So if we're talking about a car, or if we're talking about a roller coaster, an object in motion stays in motion. They have to have enough inertia to keep moving, or to get over the next hill, or something to that effect. Momentum is really just used when we're talking about collisions in science. So momentum we can define as a strength of motion. But it's a strength of motion that helps us determine what happens in collisions. That determines the result of a collision. So when we talk about acceleration, that tells us how fast something's going to be moving after a little bit of time. When we talk about velocity, that tells us how fast it is moving. Distance, how far apart things are. If we talk about force, that's talking about how much a push or a pull is. But when we talk about momentum, that's a little bit more vague. So momentum is the strength of motion, and we can calculate it based on P equals mv, where m is mass, v is velocity, and p is momentum. But when we actually calculate the momentum of something, it doesn't necessarily have a lot of meaning on its own. So we could find the momentum of, say, a soccer ball of mass 0.4 kilograms is rolling at 10 meters per second. What's its momentum? Who's got a value for me? 4. Because we can identify our variables, P, M, V. M is 0.4 kilograms. V is 10 meters per second. If P equals mv, then P is equal to 0.4 times 10, and momentum equals 4 kilogram meters per second. There is no special unit for momentum, so that means that whatever units you're using are great. As long as they all agree in the problem, use whatever you're given. But if I tell you a ball or a soccer ball is rolling with 4 kilogram meters per second of momentum, does that really tell you anything? Not really. And that's not just because momentum's a new concept for you. That's because that's not a useful piece of information. However, if we start to talk about it in terms of pairs, now it starts to be useful because momentum is a property that is conserved. So conservation of momentum. All right, conservation of momentum. We've had another thing that was conserved this year. What was it? Mass. We talked about conservation of mass. What was the law of conservation of mass? Can't be created or destroyed. It can just change forms, right? And we showed that in balancing chemical equations. We had the same number of different elements both before a reaction and after a reaction. So here, it's conservation of momentum. Momentum can't be created or destroyed. It can just be transferred. Momentum cannot be created or destroyed. It may just be transferred. All right, so let's go ahead and use this and take a look at the first problem on the worksheet that's posted on your Google Classroom. There are two categories of collisions. The first one is inelastic. And in an inelastic collision, objects that strike each other stick together. Objects stick together. The opposite then would be an elastic collision, where the objects bounce off each other. Mathematically, we are only going to look at inelastic collisions because elastic ones get tricky. Okay, so inelastic collisions are any collision where things are rolling together and they get stuck together afterwards. Elastic would be things bounce like pool balls, and that's a little harder. Okay, questions about conservation of momentum, inelastic or elastic collisions? Okay, I'm going to walk through another one with you guys. Take a look at problem 2. Anytime you're trying to do one of these, start out by figuring how much momentum do we have at the beginning. So how much momentum do each of the blobs of putty have before they're tossed into each other? Who's got an answer for me? How much momentum do each of them have? Yep, first one's 8 kilogram meters per second. How'd you get 8? 2 kilogram blob moving at 4 meters per second. Ashlyn is kind of covering all you guys today. So who's got the other one for me? What's the other one's momentum? 0. It says it's at rest, so therefore 0. So what is the total momentum then? 8. What was the total momentum? 8. Okay? See if you can figure out how fast the ball of putty is moving after they've stuck together and continued moving.